Let's move on now to part 3 of this introduction to QSAR and the methods. In the first 2 sessions, I've tried to remove some of the mystery behind the QSAR approach and show that it is the simple use of trend analysis with any measure of biological activity and chemical structure. And we've discussed the idea of a variety of molecular descriptors that can be used to evaluate trends, and the outcome of this is primarily to use trends analysis for judging chemical similarity so that we know how to group chemicals together and use them to extrapolate from the untested chemical to the tested chemical. The formal process for doing that begins in the next. Part 3 of this overview is entitled Forming Chemical Categories. I say this is formal because there are guidance documents for this. The use of chemical categories has not only been used historically for a long period of time, but it is now part of the guidance documents of major regulatory activities as well as general principles in the OECD member countries. In short, chemical categories are used to fill data gaps for the untested chemicals requiring hazard assessment. This section of the online course will be rather brief, primarily because we only need to have a good sense of what the terminology means in order to get into the use of the toolbox, and secondly because this area of work is evolving quickly and we hope to add more examples and more detail to part 3 on the use of chemical categories as time goes on. But for right now, there are only a few simple points that I think we need to make. A chemical category is a group of chemicals that have some attribute in common. The commonalities may be described in structural terms, having a common substructure, electronic properties. This would be putting all aldehydes together or carbamates together, and in fact I believe that EPA established over 130 different common categories of chemicals that are all grouped based on structure. There are ways of grouping chemicals by properties. Similar physical, chemical, topological, geometric, or surface properties. An example might be corrosive chemicals, grouping acids, grouping chemicals that have strong irritating capabilities would be those that are reactive chemicals or unstable chemicals. We might group chemicals by behavior, and in this case you could group chemicals by carcinogenicity, but in general what we have tried to emphasize in the foregoing discussion has been that if we group chemicals based on common toxicological behavior, that we should also be focusing on common toxicity mechanisms or pathways as well. And lastly, there has been a fair amount of categorization of chemicals based on what they're intended to be used for, such as solvents, detergents, fragrances, lubricants, heat transfer fluids, and so on. The point here is that there are many different ways of trying to group chemicals, or the basis for which to group chemicals and call them a chemical category. If we turn to Annex 9 in REACH, you can see for yourself that these substances, a chemical category, are substances whose physical, chemical, toxicological, or ecotoxicological properties are likely to be similar or follow a regular pattern. That's the words for basically a trend. The importance of this is that the application of this group concept requires that the physical chemical properties, human health effects, and environmental effects or environmental fate may be predicted from data for a reference substance within that group by interpolation to other substances in the group read across. This avoids the need to test every substance for every endpoint. So the heart of this effort is to say, if we can group chemicals by similarity measures that control their biological responses, then we should be able to have one or two chemicals in that category which have been tested and extrapolate those to potentially tens or hundreds of similar chemicals, even though they have not been tested, and do it well enough and with a scientifically defensible explanation to be transparent and be testable, pass the laugh test basically in terms of predictions. The OECD definition of a category is a little bit different, but I wanted to point out this comes from the OECD manual for investigation of high volume production chemicals. This was developed basically just to deal with the 5,000 or 6,000 high volume production chemicals, let alone all of the chemicals and specialty chemicals that are in production. But the OECD definition of category is a group of chemicals whose physicochemical or toxicological properties are likely to be similar or follow a regular pattern as the result of structural similarity. Again, the key words, regular pattern, a trend basically, and the result of structural similarity, and that the term similarity in all of these definitions or regulations are finessed to some extent, but they do say that similarities would create a predictable pattern in any of all of the following parameters: properties, fate, effects, human health effects. So the OECD and the EPA in the USA and in ECA in implementing the REACH all have this common approach of saying we are going to fill data gaps through the use of chemical categories. We need to form chemical categories based on similarity in order to pass the laugh test and to provide scientific transparency. So we have to come up with a way of quantifying structural similarity in a relevant manner, and that is a QSAR question. To do this involves fair amount of complex chemistry and biochemistry, and that is the purpose for developing a QSAR application toolbox. To recap, forming chemical categories, these are grouped together based on attributes important to toxicological behavior. The literature and other data sources are used to organize available data for common assessment endpoints. Once the chemical categories are formed, we used read across or trend analysis to extrapolate and interpolate from the tested chemicals to the untested chemicals. And as I said, in many cases where there's enough data, an analysis of trends can be used itself to test the boundaries of similarity for the chemicals. So it becomes a cyclical process in terms of having to make the boundaries for chemical categories more defensible. I might also point out one thing here before we go on into the work with the toolbox, and that is that the second bullet here on this slide shows that literature and other data sources are used to organize available data for the assessment point. That sounds simple, but that involves a tremendous amount of time to actually compile literature data for available information. And more importantly, it also would require that different countries be doing the same thing. In other words, there would be multiple compilations of literature data, and the effort involved in doing this was very large. So one of the intents of the QSAR toolbox is to simply facilitate the normal work of a hazard assessment, of the hazard assessment process. And part of that is in compilation of data for various endpoints that are used in these assessments. If we can compile the data once and for all, put it in a database, all referenced, so that it can be used quickly in a category approach, we would reduce lots of the effort in terms of forming categories or using them to create estimates of untested chemicals. That's the purpose of the toolbox. Let me go on. We are now at the point of trying to illustrate how the principles of the first three parts here, QSAR, terminology and processes for modeling, the use of trends analysis to judge similarity, and the creation of chemical categories, how we bring all these things together into the QSAR application toolbox. In part 4 of this online presentation, we want to look at more or less the reason for creating a QSAR application toolbox. This is meant to integrate methods that are used in everyday life, not to create anything new, but they integrate these mechanisms to improve their convenience, their consistency, and the ability to document exactly what was done if we are going to fill data gaps. In the technology transfer literature, there is a term that is a decision support system. In discussing a decision support system for filling data gaps at OECD, the discussions created certain fears that we were talking about a decision-making system, not a decision support system, and that we were trying to replace or create a black box so that you would plug in a chemical and get a number out at the end and not know how it came about. In emphasizing the fact that a toolbox should do nothing different than a hazard assessment specialist would do in his normal work: compile data, make some estimates, build categories, write a justification for the estimates, and so on. It should do only what the hazard assessor or assessment specialist would do in his normal work. And the purpose of this would be to do it faster, perhaps more consistent, that is, at least across hazard assessors and member countries, but just to speed it up and reduce the need for a hazard assessment specialist to also become a physical chemist specialist or a toxicologist, or be a jack of all trades for so many different disciplines. The idea was, can we put lots of the knowledge bases we have into an orderly fashion in the toolbox and put them at the fingertips of the specialist who needs these. That is the purpose of the toolbox, and that is why it was called the QSAR application toolbox, where in this case the application is forming chemical categories and using QSAR models, trend analysis, or read-across methods to fill data gaps. That was the application, and I want to now just turn to providing a simple overview of this prior to your getting the hands-on training. Again, let me recap why we would want to have something automated in the form of a toolbox rather than to try to do this by brute force or piecemeal. Defining category boundaries, that is, when is a chemical really part of one category and not part of another one? When are they similar? Similar enough is probably the right word. Defining chemical boundaries requires the calculation of complex attributes of chemicals to determine which attribute best explains the available data. The calculation of those attributes is arcane and is not, you don't need to know how to do that personally to be able, if you can rely on a chemical profiler that provides those to you automatically as soon as you describe which chemical you're working with. But also to determine, it says, to determine which attributes best explain the available data. Having the available data together at your fingertips instantaneously for a whole class of chemicals is really important, and that's the difficulty of doing this first bullet. It's very difficult to do, and we need to be able to speed it up and automate it as much as possible. In many cases, metabolic simulators are needed to provide metabolic maps and active metabolites for the chemicals when they are the real toxicant in the process. And again, to do trend analysis, being able to very quickly produce a graph of available data for lots of different endpoints, and then pick and choose different molecular descriptors to see if you can find trends and judge either the dissimilarity of the compound or to be able to justify particular groups of chemicals as a category needs to be done flexibly and simply. So that is basically why we need to do this. To do this manually or by brute force is just a lot of work to try to do. This toolbox that I'm showing you, basically the major window with all of the commands on it, is a toolbox. It is an application that is, as I said, devoted to or focused on filling data gaps, and it came out of a series of deliberations at OECD and ECHA, currently being funded by ECHA, but the chief developer or creator of this now is at the Laboratory of Mathematical Chemistry in Burgos, with Professor McKinnon as the lead in this project. The next slide shows a picture. I hope you realize that the staff at the Laboratory of Mathematical Chemistry changes slowly over time. This may not have all of the people associated with it currently, but I wanted to show you that there is a very large group of people in one of the most respected modeling and chemistry laboratories in the world behind the development of this toolbox. The general objectives that came out of the initial contract to put this in place was to improve the accessibility of QSAR methods and databases, to facilitate the selection of chemical analogs and categories, to try to integrate metabolism and mechanisms into the discussion of categories and QSAR, and to assist in the estimation of missing values for chemicals. The typical queries that you can get very quickly with the toolbox has been geared to some extent by a series of interviews that were done with hazard assessors in different member countries. And I remember one particular answer from a hazard assessor that when I asked, what if you are given a chemical in the morning and said, we want you to produce a hazard assessment for this chemical, what would be your first question or need? And after thinking for a few minutes, the response was, I would want to know if I am alone in this. And by that, he was saying that I would like to know what else is known about this chemical, where is it being produced, have there been other hazard assessments on this, are there experts available on this chemical that I can turn to? And answering those questions very quickly for a chemical was one of the goals. For example, taking the list of all known hazard assessments as a library, uh, taking the chemicals that are in the library of hazard assessments, perhaps, let's say what Japan did, what England might have done, what the US did, what any particular country did or group in the world did. If they did a hazard assessment, you could set just a little bit flag by that CAS number for the chemical or that structure. The instant you put in that chemical, you should be able to inform the hazard assessor who has done assessments on this chemical just instantaneously. That is simple to do if you once get it organized. So some of the queries that you can get at very quickly in the QSAR application toolbox would be, is this chemical included in the regular inventories or existing chemical, regulatory inventories or existing chemical inventories any place in the world? We ought to be able to answer that question very quickly. Has the chemical already been assessed by other agencies or organizations? We should be able to answer that instantaneously while you hit the return key. Would you like to search for available data on that assessment chemical? If you are given a chemical and have to go out into the computer, into the internet and do a chemical search and start pulling together all of the different fields that would constitute important assessment endpoints, you could be looking at a fairly long job. If we had most of the important endpoints compiled once and put into a data file on your laptop computer, then you could put in a CAS number and essentially get a literature view almost instantaneously for that chemical. That was the philosophy behind the Acquire Information System and Ecotox database, where an exhaustive reviews of the literature for specific endpoints was done once and for all and provided free of charge to all, to the public. Some of the other queries were, can we take an entire list of chemicals and find out if any of those chemicals are analogs of the chemical that we're interested in. In other words, there may not be data for the chemical we're interested in, but in the libraries of tested chemicals there may be suitable analogs. Analogs and similarity are different terminology for much of the same thing, but there are methodologies for finding analogs within certain constraints for an individual chemical that is different than going through all of the work of forming a chemical category. Generally you would get at the same point by doing so, but that is one of the requests or queries that was brought forward as an important thing for the toolbox. We would also want the toolbox to group chemicals as much as possible based on common chemical or mechanisms or metabolism or metabolic pathways. I think one of the most difficult parts of the definition of similarity in the regulations is the term whether the chemical is expected to behave similarly, which really means do all of the chemicals within a given category have similar metabolic pathways and detoxification mechanisms? Very difficult question to answer. And then finally, can we design a data matrix for an entire chemical category? Can we list lots of different chemicals and lots of different endpoints and try to array the data all in a way that's easy to interpret. So just to recap again here, that the first version of this toolbox is designed only to facilitate the work of hazard assessment specialists and those things which they would normally do in filling data gaps through the use of chemical categories. If they use predefined categories so that they don't have to worry about forming the categories, they just have to get data for the data points that they're interested in for the chemicals in this categories and do read across or trend analysis or whatever. But in many cases it may be that the hazard assessment specialists will actually have to evaluate the use of chemical categories just to feel comfortable with the estimates that are being made. Again, no attempt to replace or to automate a black box estimate of an endpoint for a chemical, but rather to allow the user to explore the data set and feel comfortable about the estimates that are made. When you turn on the Toolbox software on your laptop, you will come up with a series of 6 headings across the top, which are shown on this slide. And we think these components are a logical sequence or flow of that a normal analysis would entail. You can change and go back and forth between these, but in general you begin by telling the computer what chemical you're interested in, allowing the system to do the chemical profiling. You would then define what endpoints that you're interested in for modeling, go through a series of grouping methodologies and categories to find similar chemicals to the chemical that you've inputted, and then you would have a series of tools to do data gap filling, and then a very flexible a very flexible reporting method so that you can export this report and in a whole variety of ways so that we don't have to jump through a lot of hurdles just to inform people of the results. This then is the general flow or logical sequence for the toolbox. Let's just quickly step through each of these, and then you're ready to have a hands-on experience with the toolbox. On the next slide, I'm just going to emphasize what you would find under if you hit the button on the top for chemical input. The first step in this is to tell the computer what chemicals you want to work with, and these become the target chemical, and you can have either a single chemical or a group of chemicals. So you can put in a chemical name, a CAS registry number, SMILES or ECHI code. If you don't know any of that, you can draw the chemical structure, or you can peruse a user list or inventory and pick one. You could pick a whole list of chemicals, an inventory, and it is not uncommon to work with several thousand chemicals at the same time in the toolbox, and you'll see how quickly that can be done. Almost impossible to imagine if you try to do it on a normal spreadsheet manually. Um, what we have here is chemical profiling models where we characterize or quantify different different attributes of chemical structure. Substance information may be physical chemical properties. There may be mechanistic properties. You can customize attributes and models that you want to put in this. But there are just a whole series of either predefined or custom models that are invoked quickly and in a flexible way to give you, to let you know right away, this could be a Michael type addition. This chemical will bind to proteins, this one won't. This one could bind to the ER receptor, this one won't, and so on, and just to simply profile the chemical very quickly. Under the hazard endpoint component, this is a evolving area of the toolbox, but a lot of work was put in initially for the proof of concept version to simply compile endpoint data that are normally used in SIDS. We're calling it SIDS Plus because there are some other endpoints that are not considered SIDS endpoints necessarily, but we have all of Acquire for aquatic toxicology. We have Ecotox for the mammalian and some of the other species that would be involved in ecotox development. Bioaccumulation data, mutagenicity data, skin sensitization, carcinogenicity, the rodent repeat dose assays, and then also documented QSAR estimates that have already been done prior to your turning on the computer. The management group in QSAR for OECD is working to upgrade these databases. Our QSAR Foundation will be soon adding the inhalation database to this and other specialty databases, but this will evolve over time and just get more and more comprehensive. Moving on to the next button along the top, this is a module that allows one to form chemical categories or to prune chemical categories. By pruning, we really mean to refine the boundary conditions for the category definition. Many of these are predefined. The work has been done for us, or in some cases a category may be defined in a regulation. Those would be listed and predefined. There could be mechanistic approaches to grouping chemicals, that is, selecting chemicals that have common molecular initiating events, or something like that. There may be rather empirical methods or conventions that are used, and all of these have been defined and loaded in the system so that you can choose if you want to use an existing definition of category, or you can begin exploring a group of chemicals and an endpoint that you're interested in to see how you can best group these to make an estimate of a missing value. This next slide here just shows that some of the predefined categories here would be those defined by OECD, US EPA, substance type like aldehydes or carbamates or organophosphates or things like that, but just a refinement of the different kinds of categories that have all been already logged in and defined. When you put in a chemical structure, you should know immediately that this one or this chemical structure already belongs to a category and defined by OECD or EPA or whatever, and the basis for that. Let's go on to the final part of this is once you have a chemical category and you have some chemical members of that category that have been tested and a lot that have not been tested, the question is, how can I make a defensible estimate of the biological activity for the untested chemicals? The three approaches that you're going to learn about in guidance documents and in the toolbox itself are read across, trend analysis, and QSAR models. Again, the differences between these different methods really depend on the available data that one would have for the endpoint and the chemical group that you're working with. Read across can be done if you have 2 or 3 compounds tested in a category. If you have a large category of 300 chemicals and 30 or 40 of them are tested, then you might be able to use the trend analysis and come up with a much more robust estimate for the missing values. And then finally, it's possible that if you are interested in an endpoint that is a relatively short-term endpoint and one that a QSAR model has been built for with a well-defined domain of application, your chemical could fall right into that and you could estimate it without doing anything more. Or better yet, you could use all 3 of these methods and convince yourself how well the different approaches work for making an estimate and how variable your estimate might be for your chemical in your endpoint. But the purpose of this component of the toolbox is just to make all of these tools easily applicable to the problem that you have in the data. And finally, on the last component here that I want to talk about, the report generator for the toolbox is a really important component of this. We found in discussing with a number of industries and governments that there was a lot of time spent in formatting. That is, one set of software packages would do literature searches and report out certain data, and then that data had to be almost translated into a different format for a different computer system in order to do a certain kind of modeling. And the physical manipulation of data so that it translated from one system to the next, or from one regulation to the next, or one country to the next. The physical effort involved in that was substantial. And so we wanted to try to make sure that when you produce a report in the toolbox, it can download data in a very flexible way for many different purposes, and minimize any effort on the part of the user to have to retranslate the data or reformat the data. So you will see that the toolbox can automatically produce the reporting formats that are being used for QSAR models, reporting format, or the estimate of values. There's a reporting format for doing that, and you can basically generate that automatically. You can download data into any of the iEuclid harmonized templates. You can generate the data dossiers used in SIDS. You can come up with a complete session history from everything you've done since you inputted your chemical, complete with a timestamp on every operation, every graphic, every subset of data, every assumption that was put in to evaluate the data, and the results of that assumption in screening. Or design your own data report that you might want to tabulate for everything from a scientific paper to a assessment report for your agency. The reporting format here will be extremely flexible and should minimize the summarization of a complex array of steps. So I hope this gives you a general view of what to expect when you go into the hands-on section of the Toolbox training. We've tried to cover a general overview of terminology so that this isn't confusing to you when you first see it about 10 minutes after the course starts. It's just intended to sort of prepare you for the training course. We've tried to give you a description of how QSAR models are formed, and again to illustrate the very close ties between QSAR modeling and trend analysis, and then to also provide a brief description of how QSAR principles are really brought into this process through the judging of chemical similarity and forming chemical categories, so that you can really justify in robust scientific terms how you estimated a value for an untested chemical. And all of these being cast in the logical flow of the QSAR application toolbox. I wish you well in the course, hands-on course, and if any of you have comments on how to improve this summary or the introductory course, please send me a note here at QSARI.org, the International QSAR Foundation homepage, and we look forward to seeing you in the Toolbox.